All right, so we're going to start talking about polar coordinates and polar graphs, and this is something that sometimes we get to in pre-calc, sometimes we don't, so I think that it's new for all of you. And every graph that we've done so far has been in the rectangular coordinate system. So everything, we were plotting points in terms of x and y. And even when we had t with parametrics, we still could get rid of that parameter t and figure out what the point was in terms of x and y. So all of those graphs were still with an x-axis and a y-axis. So now we're going to look at a polar system. Instead of a rectangular grid, you have this kind of circular grid, which looks kind of cool. And before we get to that, I want to talk about some vocab. So the origin is now called the pole. And the positive, what we're used to saying is like the positive x-axis, is now called the polar axis. R would be the length of, you can think of it as a radius. So R is the length from that pole to some polar coordinate, some point P. And the ordered pair for that coordinate is R comma theta. So R, again, is the length of that little segment there, the directed distance from O to P. And theta is the directed angle, which is the positive angle counterclockwise. It's the positive angle from that initial side to the terminal side. The angles can be negative, but by default, it's a positive angle. To simply plot polar points, that's kind of where we have to start. How do I graph an ordered pair R theta? First of all, these sections that are marked off here, your polar grid could look different. They might give you more lines. This is kind of the minimum, but you can still think of this as our unit circle. So you can still think of this as 0 radians. This one is meant to be pi over 6. This is pi over 3. So on this graph, there's not an extra line for pi over 4, but some of them do that. Pi over 2, etc. So, here's pi, 3 pi over 2. So we have all of the pi over 6 and pi over 3 angles marked off on here. When you're plotting a point, you need to face the angle. Imagine yourself standing at the pole, and you're going to walk out on one of these lengths. So face the angle, and then walk either forward R units, or if R is negative, walk backward negative R units. So what am I talking about? If I want to plot the point 2 pi over 6, I'm starting at the pole, the origin. I need to face pi over 6, so I'm looking out at this line, and I need to walk out 2 units. 2 units is 1 radius, 2 radius, right here. So that's the point A. The point B is negative 2 pi over 6, so you're still facing pi over 6, so you're still facing this way, but since that's negative 2, walk backwards 2 units. So you're still on this line. See how the pi over 6 makes a line? This would be like the 7 pi over 6 angle. So you're still facing the pi over 6, but you're going backwards 2 units. So this is B. Next one is face pi over 2 and go up or forward 1 unit. So there's C. Now the next point is face negative 3 pi over 2. So remember, theta can be negative. So negative 3 pi over 2, that's still pi over 2, right? It's the same thing. And go up 1 unit. So face negative 3 pi over 2, you're still facing pi over 2. Up 1 unit means that points C and D are actually the same point. So points can have different theta and still be the same place. So points can be equivalent. There are a lot of ways. It's kind of like coterminal angles. I can tell you different ways to get there. I can make you go around the circle 100 times before allowing you to stop at whatever point I want you to stop at. And then finally, 0 and 11 degrees. Now the angle here doesn't really matter because whatever angle I'm facing, I'm going 0 units. I'm walking 0 units. So this is the pole. The angle is irrelevant. This could say 110 degrees. It could say 0.11 degrees. It could be in radians, whatever. So this point here, the pole, is E. So that's our first thing. How do we plot these points? We face the angle. We either walk forward or backward, depending on what r is. Here's what a polar graph would look like. So this can be done on your calculator if you switch to polar mode. So if you want to try this, you can switch to, let's see, right now I'm in parametric mode. So switch to polar mode. And you should keep your calculator in radians, unless you specifically see degrees. When you press y equals, now it says r. So this one says r equals 2 minus 4 sine theta. So 2 minus 4 sine. And now when you press the x, t, theta, n button, you get theta. I always zoom 6, which is just standard for whatever they're saying. Oops, what did I do? Why is this looking different? Oh, there's a 2 theta. Okay, so that's kind of cool. Notice that slight change. I forgot to put the 2 there, and I got this shape. So kind of interesting. Let me get that 2 in there. Try this again. There we go. So just that one change, the 2 theta versus theta, made a completely different shape. We are going to graph these by hand, but that is not today. All right, so coordinate conversion. Since we're not going to get into how to graph polars in their polar form right now, we do need to know the relationship between rectangular coordinates and polar coordinates, because back to these points, imagine that I laid just a standard XY plane on top of this. You could get to the point A by going a certain number of X units to the right and a certain number of Y units up. And we'll be able to figure out exactly how many units right and up, or whatever the case may be. Okay, so if we look at this as a little right triangle, let's suppose that this r theta is a point on my polar curve, or it's a polar coordinate. I can say, well, there's an x component and a y component to that. And if I use trig to solve for x, we kind of did this with parametrics, right? X would be cosine of theta equals x over r. So we can actually say that x is equal to r, whatever the length, whatever that radius is, r times the cosine of whatever theta is. And similarly for y, since sine of theta equals y over r in this triangle, then the y coordinate can be found by r sine theta. So if you're going from polar to xy, now we have a formula for how to do that. It also will be useful to be able to find r. So since we know Pythagorean theorem, we know x squared plus y squared equals r squared. We can also translate that by using substitution. I'm not going to write it all out, but we can say, well, r cosine that quantity squared plus r sine that quantity squared will equal r squared, and we can solve for r in that way. Let's put that into practice. So on the next page, we have polar to rectangular conversion. So how do we go from a polar coordinate from this to xy? So that's using the theorems that we kind of just talked about, right? So the r theta is 2 pi. So I want to get the xy coordinate. I can figure that out by saying x is r, which is 2, times the cosine of theta, which is pi. So x is 2 times -1, -2. And the y coordinate is 2 times the sine of pi, which is 2 times 0. And so the xy coordinate is -2, 0. Let's go back to our polar graph for a minute. Let's plot 2 pi and compare it to -2, 0. Let's go back here for a minute. 2 pi. Face pi, go out 2 units, walk forward 2 units, I should say. That's 2 pi. If you could lay a rectangular XY grid on top of this, can you imagine that this could also be the point -2, 0 in the XY plane? I can. It looks like it's on the x-axis, right? So, you know, there is a relationship between these two things. We're not talking about a completely different like number system or anything. Okay, what about the next one? So the next one, same process. If r is radical 3 and theta is pi over 6, then x is radical 3 times the cosine of pi over 6, which is radical 3 times, think about your unit circle, your speed quiz days. Cosine of pi over 6 is radical 3 over 2, which would just multiply out to 3 over 2. And for y, we have radical 3 times the sine of pi over 6, which is radical 3 times 1/2, which is radical 3 over 2. Okay, so our ordered pair in the rectangular coordinate system is 3 over 2, radical 3 over 2. What if we're going the other way? What if we have xy and we need to know what the polar coordinate is? So if I have xy, I can find the polar coordinate by saying, remember, we have that Pythagorean theorem, r squared is x squared plus y squared. And I don't need to change x and y. I don't need to have them like in their polar form because I already have the numbers here. So r squared is -1 squared plus 1 squared. R squared will be 2, so r will be square root of 2. Now, one extra thing I need to do, because technically r is plus or minus square root of 2, right? There's nothing that says r has to be always positive or always negative. When you're given an xy coordinate, you do need to plot the point to figure out which quadrant is it in. So -1, 1 is like right here, right? All right, so this will be important when I try to figure out theta. I have r. I need to figure out theta. So if I have an x and a y, remember these represent, like, I'm orienting this the wrong way, but these represent a right triangle, right? I have an x and a y. So I could use just tangent with the x and the y instead of having to rely on the r that I just found in case I messed that up somehow. So I can say tangent of theta equals y over x, so 1 over -1. And that's one of our nice unit circle angles. So, but it's negative. When is tangent theta equal to -1? So tangent is negative in quadrant 2, 3 pi over 4, and quadrant 4, which is 7 pi over 4. And so which one of those do I want to use? Well, the easy answer is to say, well, this is in this ordered pair is in quadrant 2. So could we face 3 pi over 4, face 3 pi over 4, and then go out radical 2 units? Yes, that would work. What about the 7 pi over 4, though? Because facing 7 pi over 4 would have you facing this direction. So what if you face 7 pi over 4? And I'm going to just label this here, 3 pi over 4 and 7 pi over 4. If you face 3 pi over 4, you go forward radical 2 units. What if you face 7 pi over 4 and go backward radical 2 units? So another possible answer is negative radical 2, 7 pi over 4. Now, there are actually infinitely many solutions when you're given the rectangular coordinate and asked to find theta, because there's no restriction, or asked to find, the polar coordinate, because there's no restriction to theta. Because of coterminal angles, I can also say, well, radical 2, and what if I add a full circle to this? So 11 pi over 4. What if I add a full circle to this one? 15 pi over 4. I could keep doing coterminal angles to land me whatever way I'm facing, and then either walk forward or backward radical 2 units. So really all of these are like plus 2 pi n nes. I'm not too concerned about that because we're not going to be just plotting these points. It'll be nice to be able to convert, but we're not going to have like infinitely many answers. But just know that they do exist. Now, it's a good idea to plot the point before you dive in. I should have done this on the first one because sometimes you don't have to do any math to figure out the polar coordinates. So for example, 0, 2, plot the point 0, 2. That's in the rectangular coordinate system, but just looking at that, I can tell you, oh, the distance from the pole to that point right there, r, is 2. Now, technically, remember, it could be plus or minus 2. R could always be plus or minus. And theta, I don't really have to do any trig. I could, but I can also just see, oh, you're facing the top of the circle. That's pi over 2. Or it could be negative 3 pi over 2. Or I could come down here on the opposite side. It could be like 3 pi over 2, or like negative pi over 2, or any coterminal angle beyond that. Okay, so just a couple of options for r theta. I always start with the angle. So what if I'm facing pi over 2? I would walk forward 2 units. What if I'm facing 3 pi over 2? If I'm facing down here, I've got to walk backwards to get to that point, negative 2. What if the angle was negative 3 pi over 2? That's really just me facing pi over 2. I'm facing up, so I would walk forward. And what if I'm facing negative pi over 2? Same thing as facing down, so I would walk backward. And again, plus 2 pi n, yes. So there are infinitely many answers there. Okay, we're going to do this last thing, and then we'll stop here for today. We're going to start sketching just a couple of basic graphs, but again, we have some more complicated things to get into tomorrow. So what do we do if it just says sketch this graph, r equals 2? If they just give you the radius, but they don't give you a theta, it means that r equals 2 no matter what theta. So r is 2 when theta is 0. R is 2 when theta is pi over 15. R is 2 when theta is 3 pi, whatever. So if you think about that, a radius of 2 units, I could plot a point here, plot a point here, or any angle in between. That would just form, mine's a little bit oblong, but that would just form a circle, right? So if you're just given a radius, that's going to be an equation for a circle. Okay, so I will connect those points with my best circle possible. There. Maybe I'll label that 2, 0. 2, 0 can be a polar coordinate and a rectangular, right? Because 2, 0 on the x-axis, but also radius 2, radian, angle 0. What if you're just given the angle and no radius? So this is saying theta is pi over 3 no matter what r. Pi over 3, let's sketch that in. That's like the 60-degree angle, right? That's like saying face pi over 3. And remember, we just talked about plotting points. That could be also facing down here in quadrant 3. What is that? 4 pi over 3, right? No matter what the radius could be 1, plot that point. The radius could be 0. The radius could be 15, negative 15, whatever. You're going to get this series of points along this line. And they would go on forever. So if you're given just an angle, that's a line. All right, and then what about r equals secant of theta? So r equals secant of theta. Remember, secant is 1 over cosine theta. And what if we multiply the cosine to the left side so that it's r times cosine theta, and then it would just equal 1? Well, remember back on the previous page, we said x is equal to r cosine theta. So now I can use substitution and say, instead of r cosine theta equals 1, I can actually say x equals 1. That's a vertical line. And it's a vertical line through x equals 1. So that's kind of cool. If that would have said r equals cosecant theta, then I would have had r sine theta. That would have been y equals 1. So that would have been a horizontal line. So kind of some interesting things. Again, to be honest, we don't do a lot with just this. You will see like r equals something. You will get just straight circles on the AP test, but not as many lines, but just kind of an interesting thing to know. Tomorrow, we're going to learn how to sketch this graph that we saw in our graphing calculator. We're going to figure out how to do that by hand. Okay, that's it for today. I think we've got textbook homework tonight.